Today we're going to be talking about geological time. We've already sat some labs already, which we've talked about how we reconstruct geological histories by understanding relative time. I'll also talk a bit about how we determine absolute time, so we're able to say something is 40 million years old, rather than just something is older than something else. I've forgotten my laser, so I'm going to have to keep coming back here so I can point to things with the mouse. The reason why we want to establish age essentially is that we want to recreate a story. We want to know what's happened to the Earth over time. We want to know how long processes take, so timescales that different processes act on. And we can look at some processes today, so we can go to a beach and examine how quickly sand accumulates over time and gets buried. We can do that. We can monitor rates of erosion by looking at them day to day, year by year. We can reconstruct, to a certain extent, records of earthquakes, but only really since records began, so the last 100, 200 years. But there are lots of things we can't really look at in a modern context, so we look to the rock record to tell us about geological processes, to tell us how planets evolve, how continents evolve, how islands evolve. We look to the geological record. So we need to have some sort of grasp of timescales and ages and relative ages if we're going to do that. So here are just some examples of the different timescales that different processes act on. So obviously a meteorite hitting the Earth, that's seconds. Some volcanic eruptions, we're talking seconds, tens of seconds, maybe minutes. And obviously an earthquake is a matter of seconds. Whereas the production of oceanic lithosphere at these mid-ocean ridges, and then its destruction at subduction zones, but all this crust on Earth is, ocean crust, is about 200 million years. So we're talking very much longer timescales for the evolution and the life of a slab of oceanic crust. And obviously continents, the breakup and the reconstruction of continents, that's even longer timescales. And this is the most important thing. Establishing the timescales that different processes act on and the ages of those rocks. They allow us to build these stories. They allow us to set dates in our stories. All of our understanding about how our Earth evolved and how our planet is changing and how maybe we're entering a new epoch where climate is incredibly different because of what we've done to it. They're all about understanding Earth processes and the timescales that those processes operate on. And just to give you a reminder about these two terms, relative age is saying something is older than something else, or something came before something else. Absolute age is saying something happened 2 million years ago, and then something happened 1 million years ago. So putting actual numbers, so absolute numbers, on our stories. So the first thing I want to talk about relative age, really. So looking at stratigraphy. So remember when I talk about sedimentary rocks, I talk about layers or beds. So the geological term for that is strata. So So we talk about strata in rocks. And so the study of strata and the relationship of those strata to each other is called stratigraphy. So by looking at those relationships between the strata, we can figure out the relative ages of the processes that form those strata. And you've all had a go at that in the labs this week. Well, last week. This week. And then I'm going to talk about radiometric dating, which is also known as isotopic dating, which is using knowledge about the decay of certain elements over time, the radioactive decay, and the products of that decay to determine how old that rock is. So I'll go into that in a bit more detail. And then I'll just go back and talk about our geological timescale and just what it looks like with those numbers. So first of all, I'm going to talk about stratigraphy, the study of strata, in order to determine our geological stories. And this is quite a famous man in the history of geology. His name is Steno. I think his first name was Nicholas. He was an Italian bishop with an interest in geology. And he came up with a set of rules. So the first two rules are his for determining the order that things happened in our strata. And a man called William Smith came along and came up with this rule. And I can't remember who came up with that one, but that's the rule we abide by when we're putting together our geological story in our stratigraphy. So I mentioned this already in the lab. So sedimentary layers collect under gravity on the Earth's surface, which means they form nearly horizontal layers in the primary stage. And then when they're buried, they'll form really nice near horizontal beds of rock. So if we start seeing beds that are being tilted, this is our lava sandstone. You can't really see it, but the strata are tilted. They're no longer horizontal, they're dipping that way by about 10 to 20 degrees. But we know that that deformation, the processes that tilted those beds, or folded those beds, that came after the beds are deposited, obviously, because beds aren't deposited like that. So if we were to talk about a basic geological history here, we'd say, okay, our sedimentary layers are deposited, and then there was an episode of deformation, where our beds were uplifted and tilted, and then the whole lot was eroded so we could see it. And the second rule this Steno character came up with was that sounds obvious to us now, but if we have a sequence of beds that hasn't been disturbed or overturned, ignore that for now. The oldest beds are always on the bottom. That's because sediments accumulate on top of each other. You can't put a sediment underneath another layer of sediment. Sediments accumulate on top of each other. So we've got a nice shale here, so fine-grained sedimentary rock. A limestone maybe deposited on top, and we run out of clay material being supplied to the ocean. Got a nice siltstone here. This is always the oldest, and this is always the youngest. So we go oldest to the youngest in a sedimentary sequence. So this is just what they might look like in reality. So we've got a nice, this is in the Grand Canyon in Arizona in the USA. So our oldest rocks are found down here. You can see these nicely exposed strata. Erosion of this canyon has exposed the rocks for geologists to study. And we've got progressively younger and younger strata, and the youngest strata on top. So by studying the rocks in this sequence, maybe studying the fossils within them, studying the nature of the sediment, so reconstructing our paleo environment from here. And from here we can create a nice story. So these are desert sandstones, they're well-rounded. They contain cross-bedding, they contain evidence of wind erosion. And then up here we have a limestone. We know our geological story would start, okay, we had a desert environment. And then for some reason sea level came up, all the crust went down, and we had a marine environment, which was probably tropical, clear waters, shallow waters, because we have marine limestone. It's all about building this story. Yeah, the oldest rocks are at the bottom, and the youngest are at the top. The word super planes on top or above, and the position obviously means position. And even if the beds aren't horizontal anymore, they've been deformed and tilted or folded, we can still mentally restore the oldest and youngest beds. So imagine these beds were once like this, and they've been tilted. We can say these are the oldest, and they get progressively younger towards the top of the sequence. So this is another famous figure in the history of geology. His name's William Smith. I believe he was Welsh. Someone told me he was, so I'm going to go with that. But he was British anyway. And what his job was, he worked on the canals. So in the UK and various other places around the world, people created artificial waterways where they take canal barges, so boats would transport produce and goods from one city to another, even if there wasn't a river there before, they create artificial rivers anyway. So it involved digging and excavating a fake river, essentially, to move a boat down. So obviously, to do that, you needed to know something about the rock, because certain rocks weren't suitable for building canals on. So William Smith was in charge of designing these canals, and he also really enjoyed looking at rocks. He became fascinated with it. And what he noticed was that, he noticed these strata, these nice sedimentary rocks lying on top of each other, but he also started looking at the fossils found in those rocks. So when we use the word fossil, it means just evidence of ancient life. It could be a footprint, it could be an actual shell, it could be an imprint of a shell. But he started drawing and describing these fossils meticulously, and he found that there was, wherever it was in the country, you'd see a certain group of fossils in one layer, and then in the second layer, in the next layer above it, you might see one of those fossils disappears. And they always appeared in a predictable order. And this is because we know now, and we can see it in the modern day, things have become extinct, and they disappear forever. And you can see that in the rock record. And so he made notes, meticulous notes about the sequences of fossils he saw in rocks throughout the UK. He found they were incredibly predictable. So the very oldest rocks in the UK contained trilobite fossils and ammonite fossils. Trilobites are like giant woodlice. You have woodlice here. They're big arthropods. I haven't got a photo of them. Ammonites are the big whirl-like shells related to the modern-day nautilus. You've seen a nautilus. Anyway, and in the progressively younger rocks, he saw more different and more different and more different groups of fossils. And he noted all them all down and allowed him to match rocks in one place to rocks in another place in terms of age. And we call that correlation. So he saw a hill somewhere in Wales and he saw a certain group of fossils, and there was a hill somewhere else in England. He could say, okay, even though they're in different places, they might be slightly different marine rocks. One's a limestone, one's a sandstone, but we know they're the same age because they contain the same fossils. So let's say this is an outcrop. Somewhere on the land, this is another outcrop. And this layer at the top, layer 1, contains, you can see a nice ammonite, a nice gastropod, a nice fish, 2 different types of bivalve, and obviously he'd have described the species, he'd have distinguished that type of gastropod from another one. And this layer here, they contain another group of fossils, so they might contain the same species of ammonite, but actually they contain a slightly different gastropod, different types of bivalves, and also a leaf fossil, a certain tree. And if you see that group of fossils in another layer, you can match them up and say they're the same age, even if they're not in the same place. I'll post some notes online about this. It's a lot easier than these diagrams make out. Oh, and this is the trilobite, the giant woodlice that I talked about before. These ruled the seafloor for hundreds of millions of years. They were the most common fossil type in the Paleozoic. They're really interesting and they grow huge. So if we're going to use fossils to match up groups of rocks in one place to another, okay, they have to have certain properties. We call these fossils index fossils. So they have to be distinctive. We have to be able to describe them in all these different places. Ammonites are really good because they can come in loads of different types of forms. so we can describe them really, really easily. Okay, they can't be some sort of organism that only lived in a very specific environment, because the chances are you won't be able to match it up between rocks. You need something like an ammonite, which lives throughout the world's oceans. You can even match species of ammonites in Australia, species of ammonites in the UK, because they were so widespread. They obviously need to be abundant. In terms of preserving fossils in the rock record, I think it's like 1% of all species was ever preserved. Most things get broken up and decayed, so the chances of creating a fossil are quite slim anyway, so you need lots of these organisms to begin with. They need to be found in different types of rocks. And ideally, I won't go into this too much, they need to evolve and become extinct in a short period of time, so we can say, okay, we see that, we know that it was formed, this rock is early Cretaceous in age, rather than something that lived for 500 million years and doesn't help us. And I just thought I wanted to show these pictures just because I think they're amazing. So these are these ammonites. So I hope you all know what a nautilus is. You see nautilus shells being sold all around Fiji. They're a type of cephalopod, and they have a shell which is whorl-like, and they're related to the squid. So they have these tentacles that come out of the aperture of the shell. So they're a distant relative of the ammonites, and that's a giant ammonite fossil found in the UK. And there are hundreds of them found in these caves. They swim through the ocean and they die, and their shell could be fossilized. Anyway, after William Smith started this study, he became a little bit obsessed by matching up all the rock types in the UK and relating them to each other in terms of age. So he knew exactly where the oldest rocks were, just by using those Steno's principles of stratigraphy. And he knew from his records of different fossil types in the rocks, the patterns, the sequence of fossils you see somewhere else can be related to a sequence somewhere in another place. And he created the first geological map of the UK. So this original map, the absolute original, was rediscovered a couple of months ago. They thought this was the original, but there was another one before it, and it's just priceless. It's one of those amazing scientific artifacts. But a geological map is essentially a map where the colours denote different rocks that are found at the Earth's surface. Forget everything underground, it's the rocks that are found at the Earth's surface. And each of those colours denotes a different rock type. And then on the side, we have a key, and we've always put the oldest rock at the bottom. But these aren't rocks, these are groups of rocks, formations, groups, etc. And he created this first beautiful map, geological map of the UK, which at that point was incredibly important for engineering more than anything else, because engineers could know where the good rock to build on was found, the bad rock to build on was found. If they want to quarry a limestone that's particularly good for building houses, they know where to find it. So this was quite important at the time. And actually after Smith had started meticulously describing and drawing these fossils that he found, the field of paleontology, which is the study of ancient life, the study of fossils, this was really, really born. People had studied fossils for a long time, but after this, people really, really started becoming obsessed with it. Universities were funding studies in paleontology, and it became the field that it is today. And it's quite interesting. I can't remember the name of the book, but there is a book which talks about the history of paleontology as a study, and it's quite entertaining. It talks about rivalry between different fossil collectors, and if you look up on, just Google it, the Bone Wars, that's a hilarious story about two American paleontologists who were competing with each other to find and describe as many dinosaur fossils and mammal fossils, I think, and they'd just be really mean to each other, and one would like plant fake fossils somewhere to ridicule the other. It's hilarious. Anyway, that's a good book. So when we were in the field, for those of you who were there, when we were in the Namosi Creek, I talked about how, okay, the geological record isn't continuous. So if you look around you and see the peninsula, okay, we're standing on rock, but we're not depositing rock, we're actually eroding it because we're on land, and most erosion takes place on land. So we have these gaps in the geological record where no sediments were deposited. Or we have gaps in the rock record where sediments were deposited, but actually they were then eroded back down again. So we have no evidence between certain rocks and other rocks of what happened in that period at that particular place. And we call these gaps in the geological record where they're essentially an erosion surface, where rocks have been eroded away. We call that an unconformity. So where we have rocks present, they've been eroded back, and then more rocks have been deposited on top, then we call that erosion surface and unconformity. And this can happen for various reasons. So say you have a nice shallow marine environment, you have sediments collecting, and they're being buried to form rock, and then maybe you have an episode of compression, and those rocks are now pushed up on land, they're eroded down. Then maybe there's a rise in sea level or crustal subsidence, and you go back into the marine environment and more rocks are deposited on top. Or you have sediments being deposited, forming rock, and then there's a global sea level drop, and so you can erode down those sediments and you end up with another gap in the rock record. Erosion always tries to go down back to sea level. Rivers are always eroding down to sea level. Anything that's exposed on land is prone to erosion. Not necessarily eroded, but it's prone to erosion. So just an example in a cartoon, what I just said. So if you look at the top diagram, sedimentary layers A, B, C, D forming in order. All of a sudden we have uplift because maybe we've got compression, or maybe there's another reason. But now it's exposed to erosion. River erosion, chemical weathering, wind erosion, glacial erosion, and we wear away layer D, for example. But then, maybe we start depositing sediments again. Maybe it now becomes a shallow sea, there's a bit of subsidence, and a new rock layer forms E, but D is missing. So that's an example of how it can happen. And there are certain names we give to different types of unconformity. So if the beds above this erosion surface are roughly parallel, this usually happens when we simply have a sea level drop. So we have nice horizontal layers, sea level drop, erosion, more horizontal layers deposited on top. That boundary would be roughly parallel. We call that a disconformity. Obviously, if the beds below the unconformity are igneous or metamorphic, they don't have layers in them, and we can't tell if the layers are parallel or not. So we call that erosion surface, in that case, a non-conformity. These are just terms you might see. But the most spectacular example of an unconformity, most dramatic if you like, is called an angular unconformity. So this is where you have an unconformity. So this is the ancient erosion surface. And below the unconformity, our beds are dipping at a different angle than the ones on top. That's why we call it an angular unconformity. And this can form because if we have our nicely horizontally layered beds, but then they're prone to deformation, which causes folding or tilting, and then those rocks are eroded down, and then if new beds are deposited on the top, you can see how these beds are now being cut. They look like they're being cut by this rock, but they're not. So we have rocks below the unconformity that are tilted, and the ones on top are dipping at a different angle. And this is just an example in the field of nice sedimentary layers. And then we have some more sedimentary layers, but they're orientated slightly differently. And this surface here is our unconformity. So these beds would have been deposited horizontally, they were then tilted or folded, they were then eroded down, and then new sediments were deposited on top. Just another example. I can't really cut high So this is our angular conformity, this is our erosion surface, our unconformity. These beds you can see here, they're dipping towards the left-hand side. And we've got nice, more recent sediments on the top. So if we create a geological story here, we can say these sedimentary layers are deposited. The oldest ones are here, the youngest ones are here. The area was then experiencing some sort of force which caused it to be uplifted and tilted or folded. Maybe there's a fold over here. In fact, yeah, it looks like there's a fold over there. And then those beds were eroded back down, and then new sediments were deposited on top. And then the whole thing was eroded so we could see it. The Grand Canyon has a really famous example. I'll show you these in the next exercise. Right at the bottom of the Grand Canyon, we have these nice, steeply dipping, really, really old rocks. So they're Precambrian in age. And then there's an angular unconformity above which the rocks are deposited. And this is what it looks like in practice. Horizontal beds above the unconformity, steeply dipping beds below it. And just some more examples here. So dipping beds, erosion surface, sediments, folded beds, erosion, just cut those beds, and then more sediments. Sediments deposited, sediments tilted, sediments eroded, new sediments put on top, and the same here. So again, reconstructing the story, so deposition of the lower beds, deformation causing tilting, erosion, and let's start erosion, then deposition of upper beds, and erosion of the landscape. And it was actually really important in the history of geology as a subject. There was a British geologist called James Hutton who came up with the theory of the principle of uniformitarianism. And he observed a lot of modern day processes. He observed erosion, he observed how sediment was washed down in a river and deposited at beaches, and he started thinking, these processes are so slow, and yet we see ancient sedimentary rocks, meters and tens of meters thick on land that I know formed from the accumulation of beach sand or whatever sand. But those processes are so slow, the Earth can't be however old people are telling me it is, it must be much older. To form the structure I see on land, it must have been much older. And he actually saw an unconformity in Scotland that looked much like this. He was already aware that layers could be tilted by tectonic forces. He didn't call them tectonic forces then. So he was convinced that the Earth must be quite old because the time it must have taken to deposit all of these sediments very, very slowly, for them to be buried to form rock, for them to be somehow tilted, then eroded. He looked at the speed of modern erosion processes, and then for more beds to be deposited on top, he thought, Earth forming processes are incredibly slow, and I think the Earth is much older than it is. So another principle, which is quite simple and obvious, is that if you see a stratigraphic sequence and something cuts through it, so a dike. So remember, a dike is formed when molten rock, magma, pushes its way into the surrounding rock, either through a pre-existing joint or it forces the rock open because it's under pressure, and then it solidifies to form a dike. The thing that cuts through the sediments must be younger, right? Because these had to be there first, and this is one. The same with a fault. Here we have some nice sedimentary layers. This fault, which is cut through the sedimentary layers and moved them, must be younger than the sediments, because it cuts through them. And so this is the principle of cross-cutting relationships. If a rock or a fault cuts through another rock, it must be younger than it. So I gave this example in the labs. Here are some nice sedimentary layers. And we have a series of dikes cutting through those sedimentary layers. So the dikes must be younger than those sedimentary layers. They must have come afterwards. However, which dike is youngest? younger than the sedimentary layers because it cuts through them. However, it's cut by dike B. The dike B must be younger than dike C. However, dike B is cut by dike A, so dike A actually must be the youngest dike because it cuts through dike B, which we know is younger than dike C. And all of them are younger than the sedimentary layers. So if we created a geological history, we'd say deposition of red, yellow, limestone, brown, yellow, brown, shale, that. Intrusion of dike C, intrusion of dike B, and intrusion of dike A. And this shows a really nice example. Say we had a cliff face, and we had this situation exposed. It looks really messy, but as geologists, hopefully now, we can say, hey, the first thing that must have happened is those beds were deposited horizontally, because all sedimentary layers are originally horizontal. Then they must have been folded at some point. We've got some nice folding. But then they must have been, they're cut by two things. Those sedimentary layers are cut by two things. This igneous intrusion here, so you can see a nice dike cutting through the sediments, and this fault. However, the fault cuts the dike, so the fault must be younger than that igneous intrusion. The order would be accumulation of horizontal sedimentary layers, folding, intrusion of large amounts of magma, and then this dike coming off this magma chamber, and then faulting, which cuts that dike. Basically, through all these principles that I just explained to you, faunal succession, law of superposition, etc., people started building the geological timescale. So even before we knew about millions of years and billions of years, we still had an order in which things happened in our heads and wrote down. And we created this geological timescale which I've shown you before. This is the oldest time period on the left, and the youngest on the right, so this is the present here. You can see a nice man here. And we separated that time into different eras, which then can be subdivided into different periods, which were then subdivided into different epochs. So there's a whole era missing here. On the left, that's the Precambrian. We don't find many fossils in the Precambrian. We find like microbial fossils and a few others, but not many. That's why I haven't included it here. But the Phanerozoic, so Phanero means visible. Do you remember phaneritic? Visible crystals. So Phanerozoic means visible life. So we see a lot of fossils, and this is the timescale of the Phanerozoic. Zoic means life, so think of zoology, zoo. So the eras are divided according to the types of life that we see in the geological record. So Paleozoic, this means old life. Whenever I use paleontology, paleocurrent, it just means ancient, or ancient life. Mesozoic means middle life, and Cenozoic means new life. And then those are subdivided into periods, and each of those periods has a distinct association of fossils with it. For example, the Ordovician is when we start getting a lot of invertebrates involving in the ocean. The Devonian, we have loads of weird fish fossils everywhere. But a lot of these periods are separated because we have a mass extinction. So basically, like 60% of existing species of fossils die out and they're never seen again, but all at once. And that happens throughout the Earth. And if you study biology or if you're interested in climate change, you think we're going through the sixth biggest mass extinction now. The rates that we see species disappearing in the modern timescale is more rapid than we see in the geological record at any one point. And this is what I did my PhD on, the end Permian mass extinction. They reckon about 95% of species died out then. We're still not entirely sure why, but literally above certain levels on the crust, around 250 million years ago, above certain layers, most of the fossils you see below that disappeared. And entire reef systems with specific species of coral, brachiopod are never seen again in the geological record. And you're probably familiar with the mass extinction event that happens at the end of the Cretaceous. This is when all the dinosaurs disappeared. Anyway, to remember those periods, there's a lot of names here, and you could develop mnemonics, so cold oysters, so Cambrian, Ordovician, Silurian, Devonian, Permian, that's what I'm referring to. Cold oysters seldom develop colourful pearls, the juices congeal too quickly. That's one way of remembering them. Yeah, that's just the old names, used to be tertiary and quaternary, what are other names, tertiary and quaternary. Well, camels often sit down carefully, perhaps their joints creak. And then this even includes a list of the epochs and the Cenozoic. Atmospheric oiling, Macaronka, there are various ways you can remember these names. And Cambrian is named after Wales. Canberra is the old name for Wales. So this Paleozoic old life, and this was dominated by invertebrates that lived on the seafloor. We didn't have life on land at this point. No land fossils are found, no land plants, nothing, no spores. These are trilobites. You can find thousands and thousands of them in marine sediments. So the Mesozoic, this is where dinosaurs dominate. So a lot of our predators are vegetarians. They're all different types of dinosaurs, and they rule the earth for a long period of time. And this is where we start developing the first flowering plants. It's hard to imagine not having plants with flowers on them. That was a major adaptation in plant evolution, was the idea of having flowering plants which spread seeds, trap insects, etc. And this is where birds evolved as well. And then the Cenozoic, this is where we start getting our mammals, of which we are one. And the oldest mammal on Earth, it's thought that everything came from sort of shrew-like characters. And back in the Eocene, we find horse fossils. So the horses are about this big. And then through time, horses get bigger to what we know horses are today. But you can trace that through time. So you can see the change in our mammals as we go through time. Anyway, I hope I won't run over time. But okay, I'll move on now into absolute ages and how we actually put numbers on things. There's too much to cover in this one lecture, so I will ask you to read the textbook, or the chapter of the textbook. I think it's chapter 8, to get a bit more information. But the most important advance in understanding the story of our Earth was when we discovered radioactivity, and from that we could develop what we call isotopic dating, or radioelectric dating. So in the late 19th century, it was discovered that certain elements, so the nucleus, certain elements, so remember our nucleus contains protons and neutrons, and remember I told you that an element is defined by the number of protons, but actually that atom can have different numbers of neutrons, and we call those different isotopes of that same element. Remind yourself what an isotope is. There are certain isotopes of certain elements that are unstable, and with time, at a constant rate, they will emit a particle which will actually change the number of protons in that atom, so it becomes a different element. And we call that radioactive decay. It happens at a constant rate. We call the initial atom, which is unstable, a parent atom, and then we call the atom that forms from it a daughter atom. And this man here, Ernest Rutherford, in 1905, applied that method, or applied that thought to dating rocks, and everything blossomed from then. The principle being, and I'll talk about that in the next few slides, whenever you have lots of elements in the system, say in a magma, but when we use magma as an example, cools and solidifies, those elements are now trapped in that mineral. And if there are any unstable elements in their atoms in that mineral, they will start to decay over time. And that happens at such a constant rate, what you can do is you can measure the concentrations of daughter atoms and parent atoms, and obviously over time there'll be fewer and fewer parents and more daughters. And you can use that to figure out how old the rock was. I'll talk about that in a second. And people started applying it to all manner of rock materials. And in 1956, Claire Patterson radiometrically dated a meteorite and found it was 4.56 billion years old. So that's where we think when we think the Big Bang happened anyway. So the half-life, I've told you that a parent atom can decay into a daughter atom. So the time taken for half of those parent atoms to decay into daughter atoms is called a half-life. And the easiest way to imagine it is it seems funny getting rid of half every single time. But imagine having a set of 100 coins, and then you toss them all on the floor, and then you get rid of all the tails. And then you take these coins, and you shake them, and put them on the floor, and you get rid of all the tails. And you keep doing that. You're always getting rid of around half every single time. So your graph will look something like this. That's the best thought experiment I can come up with to imagine this. But I'm going to use the example of rubidium-87. So rubidium is an element with 37 protons in its nucleus. Anything with 37 protons we call rubidium. The most common form of rubidium has 48 neutrons in its nucleus as well. However, there's one isotope of rubidium, which of course has 37 protons, but it has 50 neutrons. Protons or neutrons give an element its mass number, you add those numbers up. So we call this one rubidium-85. This is stable. And we call this one rubidium-87, and this is actually unstable. So what happens in a rubidium nucleus is that over time a neutron will radioactively decay, and it will eject an electron. And this produces a proton, which actually changes it. So now, because it's got a different number of protons, it's called a different element. So this is now strontium-87. Different atoms decay in different ways. There's lots of different types of radioactive decay. And what always happens is some sort of particle is emitted from that unstable nucleus, and a new atom is formed. And the half-life of rubidium-87 to strontium-87 is about 47 billion years. So we can measure this in the modern day and extrapolate it. And that's the graph that illustrates this half-life that I was trying to explain. So this is at time 0, and then this is various times in the past, the number of half-lives. So after 47 billion years, you'll have half number of rubidium-87 atoms in a given sample. And this is great for dating rocks because this graph, you can change the temperature, the chemistry, the pressure, it always looks the same for rubidium. So no matter what has happened to that rock, that process will have always been constant. So how do we do it? We've got quite sophisticated mass spectrometers now, which can measure down to individual atoms. So we take a mineral or a rock, a mineral in a rock, and we measure the number of rubidium-87 and strontium-87 atoms, and we look at the relative amounts of those atoms, and then we find the age of the rock. Now, of course, we need to know the starting number, but we can do that by looking at natural systems and looking at other isotopes in the system. So we can look at the number of, don't worry about this, strontium-86, and that tells us how much 87 there would have been in the natural system, etc., etc. But that's really important. We need to know the initial concentrations. We also need to know the half-life. And when we talk about age of the rock, what we're actually talking about is the time since that mineral was sealed. So since that mineral stopped exchanging elements to the surroundings. So that happens when magma cools and solidifies. The problem is, it can also happen if you metamorphose a rock, so you change its mineralogy. You date that metamorphic rock. What you're actually dating, in many cases, is the date when it was metamorphosed, not the time it formed initially. So you have to be really careful. But it's still really, really useful. These are some of the oldest rocks on Earth, found in Canada. They're about 4 billion years old. And different elements, that there are lots of different isotopes that produce radioactive products. Some of them are listed here. Depending on the half-life, they can be used to date rocks and materials of different ages. Now these isotopes are only found in some certain minerals, so uranium, which is a very, very useful one, uranium-238, quite often found in zircons. It's a mineral called zircon, which is common in igneous rocks. And apatite, for example, which is a phosphate, calcium phosphate. And then these are the minerals that some of the other elements are found in. So rocks containing muscovite, potassium feldspar could potentially be dated by rubidium-87 methods if they were in the right age range. So because of the different half-lives, so rubidium strontium dating can only really be used for rocks about 10 billion to 4.6 billion years ago. Whereas look at carbon-14, this is radiocarbon dating. That has a half-life of 5,730 years. So we can't really use that to date the age of the Earth. And also, it's only found in organic tissues as well. So depending on the half-life, we can use different techniques to apply this method of dating. So the ones with the longer half-lives can be used to date burial rocks. The ones with the small half-lives can be used to date much younger rocks. And even carbon-14 can be used in archaeology. And this is because, obviously, if the atoms are decaying by half every time, it'll get to a point where there aren't really enough left to measure reliably. So I'll just talk about radioparticle dating just because it's quite interesting, and you'll probably, if you do study archaeology or geography, this is quite a common method used to date material. It was used to date the Dead Sea Scrolls to however many years BC. There's the paper the Dead Sea Scrolls was on, so obviously it came from trees. And the theory behind it is, so in the atmosphere, so carbon-14 is an unstable isotope of carbon. Carbon-12 is the most stable, carbon-14 is rare and unstable. And in the atmosphere, where cosmic rays from the sun bombard nitrogen-14, they produce carbon-14, which then gets attached to oxygen as carbon dioxide in the atmosphere. So when a tree takes in carbon dioxide in photosynthesis, and it grows its tissues, its leaves, when animals or plants eat that tree, they're taking up this carbon-14. But as long as something's living, it's constantly eating and excreting, so the carbon gets exchanged with the environment. But when that organism dies, obviously there's no longer an exchange, and that's when the clock starts. So any carbon-14 atoms in me, when I die, will start decaying. And they decay back to nitrogen. The nitrogen is lost, but we know how much carbon-14 there generally is in the atmosphere at any one point, so we know our starting point. So if we measure the number of atoms of carbon-14 in tissues, like living tissues, we know how long it was since that thing died. Like I said, you can use it to date documents. So yeah, ancient documents like the Dead Sea Scrolls, fossil material. We also have carbon in bones, in skeletal material, not bones, that's calcium phosphate, calcium carbonate, we have a carbon in there. And it's generally good to use to date things up to about 40,000 years. And this is quite hot off the press. Hope I don't run over. So a couple of months ago, Dr. Holger Sommer will be giving you a guest lecture next week. Dated a bit of Gabbro, the end of Mosi Creek, and he got an age of 49 million years old, the oldest rock in Creek. And we can also do nice things. You know, I talked about understanding geological processes. So this is the Subermal. I've talked a lot about it. You looked at the microfossils in this rock under a microscope in your lab. So this is, if you drill down into the crust, where we're standing, at the thickest part, it's about 180 meters thick. And the nice thing about the Subermal is that it has lots of ash layers in it. So as that mud and calcium carbonate material was being accumulated in the ocean to form this rock, every time there was a volcanic eruption, that ash would settle out as well. And then you continue sedimentation, and another volcanic eruption, ash would settle out. So we have numerous ash layers within the Subermal, and they can be dated isotopically, because they come from volcanic material. As soon as that ash forms out of the volcano, the clock starts, and so we can date those ash layers. And so what we can do, it's a really nice graph actually, it's on a straight line. But anyway, we know that those, the lowest ash layer and the highest ash layer are between roughly 3 and 5 million years old, so the oldest is 5, the youngest is 3. We know how thick that sedimentary sequence is, so dividing one by the other, we get a sedimentation rate of 9 centimeters every 1,000 years. So, yeah, about that much every 1,000 years is the sedimentation rate of the sea floor. And obviously, the whole point is that we can get a bit more detail in our stories when we use radiometric dating, isotopic dating. Just an example here of what I talked about in the lab. So here we have some sediments, conglomerates and shales, and they've been cut through by this sill and this dike. So if we can date that sill, and date that dike, and we know that dike A is 3 million years old, and dike B is 10 million years old, so it's 70. We know that these rocks are somewhere in between the two. Sorry, I didn't get that. And also for our geological time scale, we can start putting numbers on it. So Charlie Oswald or whatever, Hamilton can sit down carefully, whatever. The Cambrian Ordovician, blah, 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 blah. We now know how long they lasted, the end date, the beginning date, all of our periods. So we can say the dinosaurs went extinct at 65 million years ago. So I haven't had time to go through these. There's only a tiny paragraph each on these in the textbook, but if you could read those, we'll cover one of them in a future lab. So yeah, if we could read through those, the slides are online. But all of these tools are really neat and they have multiple applications. And just to give you some background here, remember I told you that by looking at lava layers on land and measuring the magnetic field strength, geologists showed that the Earth's magnetic field has flipped over periodically. And because we can now date those lava layers, we create a timescale with numbers on it saying, okay, the last field reversal was 0.7 million years ago. The one before that was 2 million years ago. So by using radiometric isotopic dating, we can get a really much more robust timescale for those field reversals. We can also get a much better idea of evolutionary processes, because in marine sediments, which contain fossils, different fossils through time, or any sediments that contain fossils through time, if they ever contain a layer of ash from a volcanic eruption, or a lava flow or something that can be dated, we then can put numbers on the time those individuals were alive. And we use that in biosecurity. And then there are some other types of security. I'll leave you there. So I'll just leave you with some terms you should be familiar with. And that's about it for today. So have a good weekend.